In the last lecture, we discussed surface micromachining. The first is a definition. In surface micromachining, microstructures are fabricated on the surface of the silicon substrate by consecutive deposition and patterning of thin film structural and sacrificial layers. The silicon substrate only serves as a mechanical support and usually does not participate in the processing. We can say that surface micromachining is very different from bulk micromachining. We also compared surface and bulk micromachine pressure sensors, and we can clearly observe the difference between bulk and surface micromachining. There are two types of thin film layers in surface micromachining, structural layers and sacrificial layers. Both them are thin films. Preparation methods of thin film include evaporation, sputtering, chemical vapor deposition, spin coating, and so on. The first method we discussed is thermal evaporation, which is one of the oldest thin film deposition methods. It is based on the boiling off or sublimating of heated material onto a substrate in a vacuum. Okay. Thermal evaporation is typically carried out in a very high vacuum. Okay. The pressure is typically less than 10 to the power of -6 torr. Okay, very high vacuum. The purpose is to avoid contamination and the reaction at the source. Heating techniques. The heating techniques include resistive heating, IF heating, and E-beam heating. Among the three methods, E-beam heating is currently the dominant one. But then we introduced this very important concept for vacuum technology, mean free path. Mean free path is simply the average travel distance of a molecule between adjacent collisions. Okay, that's the mean free path. Right? The lambda, okay, the mean free path is equal to, if we use pressure in torr, okay, it's 0.005 divided by pressure in torr. The unit for lambda is a centimeter. Then we just mentioned that the evaporation pressure is less than 10 to the power of -6 torr. So at this pressure, right, we can calculate the mean free path by 0.005 divided by 10 to the power of -6. So lambda is 5,000 centimeter. It's about 50 meter. This is much greater, right? It's much greater than the distance between the source and the wafers inside the vacuum chamber. Consequently, right, the atom leaving the source can directly deposit on the wafer without collision, or without a single collision. So this is a line of sight deposition. Okay, and this kind of line of sight deposition will lead to a shadowing effect. Okay, the shadowing effect. Namely, right, there's no deposition on shadowed area. We can treat the source as a light bulb, okay? So this will be the shadowed area. Then there will be no deposition, no evaporation, okay, due to this line of sight deposition. So this is a very important feature of thermal evaporation. Okay, and this effect could be good or could be bad, right? For the good, we mentioned that, right, this is desirable for lift-up process. Okay, so for lift-up, we will choose thermal evaporation. Okay, now let's discuss the deposition rate of evaporation. It can be derived that the number of molecules striking the wafer surface can be expressed as this equation. Okay, A crucible, that's the area of the crucible, divided by 4 pi r squared. Right? R is the radius of this circle. Okay. Square root p squared over 2 pi kTm. Right? P is the pressure, the vapor pressure of the material. So we can say that there's a deposition rate is proportional to the vapor pressure. The left figure, right, this figure plots the vapor pressure as a function of temperature. The horizontal axis is a temperature. And in order to achieve a reasonable deposition rate, the vapor pressure typically need to be greater than 0.01 torr. Okay, so we can consider this as a threshold vapor pressure. In order to achieve reasonable deposition rate, the vapor pressure of the material to be deposited need to be greater than 0.01 torr. And then we can see that for aluminum, gold, nickel, chrome, titanium, right, they can reach 0.01 torr with a temperature between approximately 1000 and 1700 degrees C, okay, with a reasonably high temperature. Okay, and the platinum, we can observe that platinum needs 2000 degrees C, needs a higher temperature to reach this 0.01 torr vapor pressure. In addition, we can observe tungsten in this corner. W, right? W stands for tungsten. So we can see that tungsten has a very low vapor pressure, even at 2500 degrees C. So tungsten is very difficult to evaporate. Okay, so we need a very high temperature, and its deposition rate will be very, very small. And tungsten is known to have the highest melting point of all metals. Okay, so tungsten has the highest melting temperature of all metals. Next, let's take a look at sputter deposition. Right, this is another way to deposit thin film. Right, sputter deposition. We previously studied sputter etching. Right, sputter is used to etch, and it is very interesting to know that sputter can be used for both etching and deposition. Right? So it is not surprising that we use the same setup for both sputter etching and sputter deposition. You probably can recall that this setup is the same as the sputter etching setup. Right? Namely, we have 2 electrodes. Okay, one anode. Right? Anode is grounded. A cathode. Cathode is a powered electrode. Okay, IF IF power is coupled to this cathode through a matching network. And the sputtering target, right? The material to be deposited, right? For example, aluminum, right? If you want to sputter or deposit aluminum thin film, we place this aluminum target on cathode. And the wafer to be deposited is placed on anode. So the anode is a substrate holder for deposition. Right? Cathode is the holder for the target, sputtering target. Then the high energy ions, positively charged ions, strike on the target. Target is placed on cathode. Why do the high energy ions strike the cathode? Because the cathode has a negative DC bias. Okay, it's negatively biased, and the positive ions will strike the cathode. Okay, that's the reason. And those high energy ions can sputter out atoms of the target based on momentum transfer, physical momentum transfer, or ballistic momentum transfer. Then these sputtered out atoms deposit on the wafer placed on anode. Let's assume they are wafer placed on anode. Okay, those sputtered atoms then deposit on this wafer. So what's the difference between sputter etching and the sputter deposition? Right. For sputter etching, the wafer is placed on cathode. Right. Then the wafer will be bombarded by high energy ions. Sputter etching occurs on cathode. For sputter deposition, right, the wafer is placed on anode. The sputter target is placed on cathode. We actually can observe that in sputter deposition, etching also occurs. Okay, etching occurs on the target. Okay, then deposition occurs on anode. Right, for both sputter etching and the sputter deposition, we need to use a plasma. Okay, and the plasma generate ions. Then ions are accelerated by the high negative potential of cathode, causing sputter etching. So we can say that the physical process of sputter etching and sputter deposition is the same. Okay, the same physical process, but we just place the wafer on different electrodes. Now let me ask this question. If the pressure is 100 millitorr, right, some kind of arbitrary number, okay, it actually, the sputtering pressure actually can be less than 100 millitorr. Okay, for simplicity, let's here just assume it's 100 millitorr. Then how long is the mean free path? Well, we just use the formula we used a moment ago, right? Okay, let's double check. Lambda should be equal to right here, right? 0.005 divided by pressure in torr, right? 0.005 divided pressure in torr. 1 millitorr is 0.1 0.1 torr, right? And
yes.
the unit is a centimeter. So lambda is a 0.05 centimeter. Or 0.5 millimeter. It's a fairly short distance. This distance will be much shorter than the distance between cathode and anode. Then what do we know based on this mean free path? Right, this one is much shorter than this distance. What's the implication? We know that based on this mean free path, we know that the atom leaving the target, leaving the cathode, right, will experience multiple collisions before arriving at the wafer placed on anode, right? Unlike evaporation. For evaporation, the mean free path is a very large, right? 50 meters, much greater than the distance between the target and the wafer, okay? For sputtering, mean free path is much shorter, right? Due to the much higher pressure, there are more gas molecules, then there will be more collision. So the average distance, the mean free path will be much shorter. So is the sputter deposition line of sight deposition? No, it will not, right? It will experience multiple collisions. Okay, so let's assume, let me draw another figure. Let's assume this is a substrate, right, which has a step. Then the atoms, for example, aluminum atom will arrive it from different angles, random angle, right? Okay, randomly. So sputtering has a much better step coverage. Okay, it's not line of sight deposition. Compared to thermal evaporation, it has a better step coverage. Questions? Now let's have a brief comparison of evaporation and sputtering or sputter deposition. First, the deposition pressure. Evaporation needs very low deposition pressure, typically less than 10 to the power of -6 torr, right? Why do we need such a low deposition pressure? Why? Less than 10 to the power of -6 torr, right? Very low pressure. Right? That's because we want to avoid the contamination or chemical reaction between the source and the atmosphere, right? Between the source and the gas molecules. So we have to do it in a very high vacuum, a very low pressure. Right? Sputtering needs relatively high pressure, right? For example, tens of millitorr. Tens millitorr. Okay. Can we perform sputter deposition in very high vacuum, like for example, 10 to the power -6 torr? Can we do sputtering at a very high vacuum? Generally, no, right? Because we need a plasma to do sputtering, right? To do the sputter deposition. If the pressure is too low, then it's very difficult to generate the plasma, or there will be not enough ions generated. Right? Ions must be generated from gas molecules, right? So we cannot do sputter deposition in very high vacuum. Okay, its pressure must be relatively high. Okay. Deposition rate. Evaporation has a high deposition rate, right? Up to 0.5 micron per minute or even higher. Sputtering typically is very low. A typical number is 50 angstrom per minute or 5 nanometer per minute. It's lower than that of evaporation. Step coverage, this is very important. Evaporation poor, right? Because of the line of sight deposition. Its mean free path is very long. So evaporation has a poor step coverage. It's not able to cover the step very well. And the sputtering is good, okay, as we just mentioned in the slide. Okay, it can cover the step pretty well because of the very short, right, mean free path. So the atom will arrive at the substrate with a random angle, all kinds of angle. Alloy composition. Evaporation has a little or no control. So evaporation is not good for alloy deposition because different metals have different vapor pressure. Right, for example, if the target is alloy A and B, its ratio is let's say it's 50 to 50, okay, 50-50 A and B. After evaporation, in the thin film, you may end up with A only 1% or 99% B, because A and B will have different vapor pressure. So we typically do not use evaporation to prepare alloy thin film because of this poor control of alloy composition. On the other hand, sputter deposition can have tightly control of the alloy composition. So we typically use sputtering to deposit alloy thin film. Choice of materials. Evaporation is limited. Sputtering, almost unlimited. So sputtering has a typically wider choice of materials. Questions? Okay, next let's discuss oxidation of silicon, right? Thermal oxidation of silicon. Right, this is a method we use to grow thermal oxide, thermal silicon dioxide. To be more specific, right? Thermal silicon dioxide. The applications. The applications of thermal oxide in integrated circuit include gate oxide. This is probably the most important application of thermal silicon dioxide. I believe everybody knows structure of MOSFET, right? Okay, let's say this is a NMOS. We have source, we have drain, and then we have this gate. Initially, it's a gate made from metal. Okay, so this is the metal gate. The metal gate is separated from the channel or substrate by an oxide layer. Okay. So we call this a MOS structure, right? Metal oxide semiconductor. Right? And this oxide layer is typically made using thermal oxidation of silicon. And I said this is probably the most important application of thermal oxide in IC. And this is a very critical component of MOSFET. Thermal oxide can also be used as used for isolation, insulation, diffusion mask. In MEMS, thermal oxide can be used as an etching mask for both wet and dry etching, or sacrificial layer, or structural layer. This oxide, thermal oxide layer can be used either as a sacrificial layer or structural layer. There are two types of thermal oxidation, right? Dry oxidation, silicon reacts with oxygen gas, right, to form silicon dioxide. The second is wet oxidation. Silicon reacts with water, and we also get silicon dioxide. There are two types of thermal oxidation, dry and wet oxidations. Note that thermal oxidation consumes some of the wafer thickness, right? Namely, the silicon substrate participates in the chemical reaction to form silicon dioxide. Right? The silicon substrate is reacted. Okay. Certain amount of silicon is consumed. If we assume the total thickness of the thermal oxide is TOX, right? That's the thickness of thermal oxide, and this dashed line stands for the original silicon surface, the bare silicon surface. Then 54% of TOX is above this dashed line, above the original silicon surface. And 46 is below this dashed line. So it's very, very simple, right? So now let me ask this simple question. If we grow 1 micron thermal oxide, how thick is the silicon substrate consumed? If 1 micron silicon dioxide is formed, how thick is the silicon substrate consumed? It should be very simple, right? It should be 46%, right? So it should be 0.46 micrometer. Right, this amount of silicon substrate is consumed. So here I want to emphasize that, right, thermal oxidation, right, consumes some of the wafer thickness. Right, this is very different. It's very different from evaporation or sputter deposition, where the silicon substrate only serves as a mechanical support. Right, the thermal oxidation is typically carried out in an oxidation furnace. We call this an oxidation furnace. Right? It is simply a quartz tube surrounded by a 3-zone heater. Okay, so there's a 3-zone furnace. And we can inject water vapor or oxygen, okay, for either wet oxidation or dry oxidation. We can say this is a fairly simple setup. This picture shows a real thermal oxidation furnace. And this is the inlet of the furnace, and this is a control panel, right, to control the temperature of the furnace. Deal growth model. This model is developed by these two scientists, Deal and Grove. So we call it the DG model. This model is used to predict the thickness of oxide, of the thermal oxide, as a function of temperature. Thus, the XF stands for thickness, silicon dioxide thickness. As a function of temperature. Okay, so this T is oxidation time, sorry, not temperature, time. And the ADG, right, ADG and the BDG are temperature dependent constant, two constant, ADG, BDG. And the tau DG is another constant. So this thickness equal to 0.5 ADG times the square root 1 plus 4 BDG divided by ADG squared times T plus tau DG minus 1. Okay, this T is the oxidation time. And this model can be divided into 2 regions. At short times, so when T is very small, the square root can be expanded to yield the linear rate model. Namely, when X is much smaller than 1, square root of 1 plus X is approximately equal to what? 1 plus 1 over 2 times X. Right, this is a kind of Taylor expansion. Right? The square root can be replaced by a linear function. Right? It can be linearized when X is small. Right? Then the thickness of silicon dioxide is equal to BDG over ADG times T plus tau DG. Right, so XF is a linear function of oxidation time. At the long times, T is very large. Then compare with the second term, this 1 is negligible, and this one is also negligible. So eventually, we end up with this simple equation. Right? The thickness is equal to the square root of BDGT. So it's proportional to the square root of the oxidation time. So if we plot XF as a function of oxidation time T. Okay, let's assume this is our origin 0. Then initially it's linear. Okay. XF is a linear function of t. And eventually it becomes parabolic. Okay, so that's the XF versus t relationship. This table gives you dG rate constant for the dry oxidation of silicon. This is for dry oxidation. We have AdG, BdG, and the tau dG at different temperatures. The bottom table gives you the dG rate constant for wet oxidation of silicon. And we have AdG, BdG as well. And know that for wet oxidation, tau dG is equal to 0. So we don't need to worry about tau dG for wet oxidation. Now let's consider this example. Right, we know that this will be a homework problem. So here I give you some explanation. Let's calculate the thickness of silicon dioxide grown during 120 minutes, 920 degrees C wet oxidation. So we're going to use the bottom table, 920, right? 920 degrees C. Assume the wafer initially had 1,000 angstrom oxide, so 100 nanometer or 0.1 micrometer initial thickness. This is 0.1 micrometer. How do we solve this problem? We already have this DG model, right? And we know AdG, BdG, tau dG is 0, okay? So can we simply plug in the oxidation time T? Right, 120 minutes, right? Please pay attention to the unit for AdG and BdG. AdG, micrometer, BdG, a micrometer square per hour. So we should convert time to what? Minutes to what? Let's do 2 hours, okay? So T is 2 hours. Can we simply plug in this 2 hours into this formula to calculate the thickness? No, we cannot. Because what? Because the wafer initially had 0.1 micron oxide. It has some initial thickness. Let's use this figure to explain. Let me change the color. Initially, we're 0.1 micrometer. That corresponds to time T1. We can imagine we use a time T1 to obtain this 0.1 micron oxide. After this T1, we oxidize the silicon wafer for another 2 hours, right? So this is the eventual thickness we are going to calculate. So how do we calculate X? The time T should be what? The total oxidation time should be equal to T1 plus delta T. So this 2 hours is actually delta T. It's not the total oxidation time, it's only delta T. But in order to calculate the final thickness, this T should be the total oxidation time from 0 thickness. Right, so T should be equal to T1 plus delta T. Right, so for this problem, you only need to calculate T1. Everything else is given, right? You need to calculate the T1. Questions? Now let's take a look at this local oxidation process. In this process, we first deposit and pattern a silicon nitride layer. So this green layer stands for silicon nitride, and this is a silicon substrate. So let me label it. This layer is a silicon nitride, and this substrate is a silicon. Okay, the silicon substrate. So we first deposit and pattern the silicon nitride layer, and then in step 2, etch further into the silicon substrate. So we further etch into the silicon substrate by this depth, right? Let's call this D, okay? Then we perform thermal oxidation. Okay, we perform thermal oxidation. During thermal oxidation, silicon nitride, this silicon nitride thin film serves as an oxidation barrier. Namely, the silicon underneath silicon nitride is not oxidized. Only this exposed cavity is oxidized. So inside this cavity, the silicon is oxidized, or the silicon oxide grows and refill this cavity. So this yellow pattern stands for silicon dioxide layer. Now let's consider this question. Okay, this will be another homework problem. Assume silicon nitride is a 0.2 micron. So this thickness is 0.2 micron. If you want to have a planarized cavity of 2 micron deep, namely, the oxide grown in step 3 will have a thickness of 2 micron. Right? So this distance is 2 micron. And the top surface of oxide need to be leveled with the silicon nitride surface. How deep will you etch into silicon in step 2? So how large is D? How do you solve this problem? Actually, very simple. We know that this dashed line stands for the original silicon surface, right? Namely the surface, right? And the silicon dioxide above this original silicon surface accounts for 54% of the total thickness, right? Above this silicon surface, 54%. So how large is this distance? From top surface to this original silicon surface. Or actually it's between the top surface and the bottom surface, right? Right. These two distances are same. How large is this distance? Okay, hint.
50% of 2 micrometers?
Yes, okay. It's 2 micrometer times 54%. Okay. So that's how you solve this problem. Then you can find the D easily. So actually, I already told you the answer. Questions? Chemical vapor deposition, CVD. This is another popular way of preparing thin films. Know that in some sense, evaporation and sputtering are called physical vapor deposition. And namely, in evaporation and sputtering, they are only physical processes, no chemical reaction. So we call them, sometimes we call them physical vapor deposition. And in CVD, in chemical vapor deposition, thin films are formed on a substrate by chemical reaction. This must be chemical reaction, okay? By chemical reaction of a vapor phase reactants that contain the required constituents. Examples, the first example is the polysilicon, a polysilicon thin film. Polysilicon thin film can be deposited using silane gas, SiH4, right, silane. At an elevated temperature, silane can decompose into silicon and hydrogen. Okay, and this solid silicon will form polysilicon thin film. So this is the CVD method to deposit polysilicon thin film. Another example is a silicon nitride thin film. Right, this thin film can be prepared using dichlorosilane. Right, silane, right, 2 hydrogen atoms replaced by 2 chlorine atoms. So we call this dichlorosilane. Right, this gas reacts with ammonia. Right, both are gases. Right, it's vapor phase. Right, both are vapor phase. They react to form silicon nitride thin film. And the silicon dioxide. I know that we just learned silicon dioxide thin film prepared by thermal oxidation of silicon. Right, that oxide is called thermal oxide. And the silicon dioxide can also be prepared using CVD method, right, different method. In this method, silane reacts with oxygen and generate silicon dioxide. So the product of this reaction is a silicon dioxide and the hydrogen. So this is a chemical reaction we use to deposit silicon dioxide thin film using CVD method. But please know that in CVD, the silicon substrate does not participate in the chemical reaction. Okay, oxygen reacts with silane to form silicon dioxide, not silicon. And because of this, silicon dioxide can be deposited on, for example, metal surfaces by using CVD method. But we cannot do that using thermal oxidation. As we can see in this table, there are typically 3 CVD methods. First is APCVD. AP stands for atmosphere pressure. So atmosphere pressure CVD. Advantages of APCVD. First, simple reactor. This is obvious because APCVD does not need a vacuum. So the reactor is very simple, probably just a furnace, no vacuum. Fast deposition, low temperature. Disadvantages: poor step coverage, particle contamination, low throughput. The second type of CVD is LPCVD, right? Low pressure CVD. LP stands for low pressure. LPCVD has excellent purity and uniformity. Conformal step coverage, so pretty good step coverage. Large wafer capacity, high throughput, but it needs high temperature, and its deposition rate is low. But the third category is a PECVD. Right? PE stands for plasma enhanced CVD. Okay, PECVD stands for plasma enhanced CVD. Because a plasma is used, so the deposition temperature is lower. So it has a low deposition temperature. Fast deposition, good step coverage, but it has a chemical and particle contamination. So in terms of quality, LPCVD provides the best thin film quality, LPCVD. So it is widely used in surface micromachining. This figure shows a simple thermal CVD reactor. Step coverage. We have mentioned the step coverage many times. Now let's have a more detailed discussion of step coverage. Know that there are 2 factors that determine the step coverage, whether it's a good coverage or bad coverage. Surface mobility and the mean free path. We already introduced mean free path. Surface mobility simply refers to the capability of the molecules to move on the surface freely or rapidly. Okay, so whether the molecule can move on the surface rapidly. That's the surface mobility. Figure A, okay. Figure A shows a uniform step coverage resulting from rapid surface migration. Okay, very high surface mobility. Okay, that's the case A. Rapid surface migration. If we have a rapid surface migration or large surface mobility, then we can always get uniform step coverage, no matter how long, how short the mean free path is. That's case A. Case B plots the non-conformal step coverage for long mean free path and no surface migration. But then we obtain this non-uniform thin film deposition. And case C. Case C shows the non-conformal step coverage for short in-free path and no surface migration. So if we have short in-free path and no surface migration, we will end up this kind of profile, the thickness distribution. Let's say a few more words about case C. So let me explain why we end up with this kind of thickness distribution. That's because in case C, namely when the mean free path is very short and no surface migration, the thickness of the thin film is proportional to arriving angles. What is the arriving angle? Actually, it's very simple. For example, for this point, right, which is on a planar surface, its arriving angle is 180 degree. Right, namely, the atoms or molecules can arrive from 180 degree. On the other hand, the arriving angle of this corner is only 90 degree, right? 90 degree arriving angle. And this convex corner, right, this is concave. This convex corner has a 270 degree arriving angle. Similarly, this one, right? This node will have a 270 degree arriving angle. So if we draw the thin film thickness, then we will end up with this kind of profile. This convex corner will be thicker because it has a larger arriving angle. The concave corner is thinner, okay, and this is the 180 degree, and another convex corner thicker, okay. So that will be the thickness distribution for case C. Okay. Okay, next let's focus on a specific thin film, polycrystalline silicon or polysilicon. This is a widely used thin film in surface micromachining. As I stated here, polysilicon is the most popular structural material in surface micromachining. Polysilicon can have zero building stress and stress gradient, predictable mechanical and electrical properties. Its Young's modulus is about 160 gigapascal, 160 plus minus 10 G Pascal. And its grain size orientation can be controlled. Its electrical resistivity can range from 0.1 milliohm centimeter to intrinsic. Intrinsic polysilicon has a very large resistivity, okay, very high resistivity. Application of polysilicon. First is a structural layer, we just mentioned here. In addition, polysilicon can also serve as a conductor when it's heavily doped, and a piezo resistor whose resistance is a function of mechanical stress or mechanical strain. Okay, so if we apply stress or strain, the resistance will change. Okay, so this is a piezo resistor. So we can use a piezo resistor to sense stress or strain. Polysilicon can also function as a temperature sensor, right? Because its resistance is also a function of temperature. Okay, so we can use it as a temperature sensor. So we can see polysilicon has many important applications in MEMS. Polysilicon thin film is typically deposited using LPCVD, right? Low pressure chemical vapor deposition. Right, this is the chemical reaction where we use a silane gas, right, to decompose into silicon and hydrogen. The deposition temperature is between 500 degrees C and 700 degrees C. Note that if the deposition temperature is below 590 degrees C, the deposited thin film, the as deposited thin film is actually amorphous silicon, not a polysilicon. In chapter 2, we have explained the difference between polycrystalline and the amorphous solids. If you forgot, please go back to check your class notes. This figure shows a typical LPCVD system. The reaction, right, the LPCVD process, or the chemical reaction, is carried out inside again, it's a quartz tube, a furnace. But this furnace now is maintained in vacuum. So in the vacuum pump to generate the vacuum, or to reduce the pressure, right? Because it's a low pressure CVD. It's carried out in low pressure or a vacuum. So in the vacuum pump. And the gases, reaction gases, okay, are injected into the tube from the front end. This is the typical LPCVD system. This figure, the figure on the right, plots the deposition rate as a function of temperature. But please note that the horizontal axis is 1 over T. Okay, the reciprocal of temperature. Okay, so from right to left, temperature increases, right? If we move from right to left, the temperature increases. And know that the deposition can be broken into 2 regions: mass transport limited and the chemical reaction limited. Know that in order to form the thin film on the substrate, the gas molecules or vapor phase molecule need to diffuse to the surface. They need to be transported to the surface. Okay, so this is a mass transport process. Then on the surface, chemical reaction occurs. So that's step 2. Right? Step 2 occur on the surface. And these 2 steps, or these 2 processes, occur in series. Right? They occur in series. So the overall rate is determined by the slower process. Whichever is slower will determine the overall rate. Now let's take a look at this figure again. At the low temperature, right side, okay, at the low temperature, chemical reaction is slow, right? So ALPCVD is determined by the chemical reaction. So this is a chemical reaction limited regime. Okay, so we can see it's the deposition rate is very sensitive to the temperature. Okay, right. Chemical reaction is slow, so it's determined by the chemical reaction. When temperature increases, when temperature is high enough, chemical reaction will be faster than mass transport process. Right. Now the chemical reaction rate increases significantly. So now the slower process becomes the mass transport. So now this region is a mass transport limited region. Right. It's not so sensitive to temperature. Building stress and strain of polysilicon. Before we discuss this slide, let me give you a brief introduction of mechanical stress and strain. I know most of you are electrical engineering students, so let me give you a brief introduction of stress and strain. Let's consider the beam shown in this figure. We apply force F to stretch or elongate this beam. And its original distance or length is L naught. After stretching, its length is increased to L naught plus delta L. So delta L is the increase or the change of length. And the mechanical strain, epsilon, is defined as a delta L over L naught, or the normalized distance change. And this quantity is dimensionless, right? No unit, right? Meter cancel with each other. This is the mechanical strain, epsilon. We typically use epsilon to represent the mechanical strain. And the mechanical stress, sigma, is defined as F over A. Right? F is the force applied. A is the cross-sectional area of this beam. So mechanical stress is simply the force per unit area. Right? The unit is a Newton per meter square or Pascal. If the beam is stretched, both strain and the stress are positive, right? Because delta L is positive. Okay, positive strain and the positive stress. If this beam is compressed, right? If it shrinks, then both strain and stress are negative. Right? This is how we define the sign of stress and strain. Okay, because when it's compressed, delta L is negative, right? Delta L is negative, so the strain will be negative, stress will be negative as well. And the ratio of stress to strain is actually constant for many materials. And this constant is called Young's modulus. So Young's modulus, or it's also called elastic modulus. E is defined as a stress over strain. Okay, this is a constant. And based on Young's modulus, right, sigma is a linear function of strain. Okay, it's a linear proportional to strain. Okay, sigma is equal to E epsilon. This is actually Hooke's law in 1D case. Know that Positive stress is also called tensile stress. Right? Tensile stress, the positive. Negative stress is called compressive stress. And it's very easy to understand that tensile stress causes concave bending. Okay, because tensile, if a thin film has tensile stress, it tends to shrink. Okay, if the thin film shrinks, it will cause this concave bending of the substrate. On the other hand, compressive stress, okay, if this thin film has compressive stress, it may cause this convex bending. Okay, so this is a tensile stress and compressive stress. Okay, now let's finish discussing this slide. Building stress and strain of polysilicon. This figure plots the anneal curves of fine-grained LPCVD polysilicon film deposited at 550 degrees C. So the vertical axis represents mechanical strain. Right? The positive axis represents tensile strain. Okay, positive. The negative part represents compressive strain. And the horizontal axis is the annealing time. And we can observe that low temperature annealing, for example, this curve, low temperature, it's probably 600 degrees C. Okay. This low temperature annealing will reduce the strain, mechanical strain of polysilicon to almost zero within 2.5 hours or 3 hours. Then moderate annealing temperature, for example, 700 degrees C, 850 degrees C, rapidly reverse the strain from compressive to highly tensile. Okay, initially we know that the as deposited polysilicon thin film has a very large compressive stress. Okay, this is compressive. With a moderate annealing temperature, right, this compressive stress can be reversed, quickly reversed, and become tensile. Next, high temperature annealing. For example, 1050 degrees C, 1050 degrees C. Then we can see that the internal stress of strain can be reduced to almost zero within half an hour. Okay, very quickly. So typically we use 1050 degrees C to anneal polysilicon thin film to reduce its building stress and the strain.